Welcome everyone. Today we're going to work through the core statistical tools you'll reach for most often when comparing group means in veterinary research. The t-test, ANOVA, and ANCOVA. These aren't just academic exercises. Every clinical trial you design, every treatment comparison you publish, and every herd level intervention you evaluate will depend on choosing the right test and interpreting it correctly. The goal today is to give you a clear decision framework so that when you sit down with your data, you know exactly which tool to use and why. We'll start with the simplest case, comparing two means with a t-test, and build up to ANOVA for 3 or more groups. Then we'll finish with ANCOVA, which lets you adjust for baseline differences that can confound your results. Along the way, we'll work through real veterinary examples, selenium levels in dairy cows, body condition scores across lactation, feed supplement trials in beef steers. One recurring theme. With the small sample sizes typical in veterinary studies, statistical power is precious. Choosing the right design, especially paired designs when the structure allows it, can make the difference between detecting a real effect and missing it entirely. We'll come back to that point several times. By the end, you should be able to look at any group comparison problem, identify the appropriate test, check the assumptions, and interpret the output with confidence. Let's get started. T-test is the simplest and most commonly used tool for comparing means, and understanding when to use each version is fundamental. The t-statistic is a signal-to-noise ratio, numerator, the observed difference between means, the signal, denominator, the standard error, the expected random variation given your sample size and data spread. A t of 3 means the signal is 3 times bigger than the expected noise, unlikely to be chance, hence a small p-value. The paired design is the version most often underused. When you measure the same animal before and after an intervention, or when animals are matched across groups, each animal serves as its own control. You calculate the difference for each animal, then test whether the average of those differences is different from 0. Because individual baseline differences are canceled out, the error term is much smaller and the test is much more sensitive. If you have the option of a paired design, use it. With small veterinary samples, the power advantage is often decisive. 2 worked examples. Let's walk through both calculations step by step. A 1-sample t-test. The standard error is SD divided by the square root of n. 14.2 divided by root 12 equals 4.1. The t-statistic is the observed mean minus a reference value divided by SE. 58.3 minus 70 divided by 4.1 equals negative 2.85. With 11 degrees of freedom, p equals 0.016. The confidence interval runs from 49.3 to 67.3, entirely below the reference threshold of 70. This herd has a meaningful selenium deficiency. The CI confirms both statistical significance and the clinical magnitude. The true mean is probably between 49 and 67 micrograms per liter. Paired t-test. Calculate the body condition score difference for each cow, calving BCS minus dry-off BCS. Take the mean of those differences, negative 0.43. The SD of the differences is 0.21. SE is 0.21 divided by root 10 equals 0.066. T equals negative 0.43 divided by 0.066 equals negative 6.5. P is less than 0.001. The confidence interval runs from negative 0.58 to negative 2.8, entirely negative. Body condition score declines significantly from dry-off to calving. Notice how large the t-statistic is despite only 10 animals. That's the power of the paired design. Individual variation in baseline BCS has been completely canceled out. Have three or more groups to compare, running separate t-tests for every pair is statistically indefensible. With four groups, that's 6 comparisons. Each carries its own 5% false positive risk. Together, the probability of at least one spurious significant finding is 26%, worse than 1 in 4 odds. You haven't done more rigorous analysis, you've inflated type 1 error to the point where your findings are unreliable. ANOVA solves this by testing all groups simultaneously in one omnibus test. One F statistic, one p-value, 5% type 1 error rate maintained. The mechanics. ANOVA partitions total variation into two components: between group variation, how far the group means are from each other; within group variation, random scatter among animals in the same group. F is the ratio. When the null is true, both components estimate the same background noise and F hovers around 1. When a treatment effect exists, between group mean square gets inflated and F rises. The limitation. A significant F tells you at least one group differs. It doesn't tell you which. That requires a post-hoc test. Choose before you look at the data. Choosing the most liberal test after seeing the results is p-hacking. ANCOVA is an elegant solution to a problem that's common in veterinary trials with small sample sizes. Even after randomization, chance imbalances in baseline characteristics occur. If those baseline characteristics also predict the outcome, they confound the comparison between groups. Imagine you're comparing 3 calcium supplementation protocols in fresh cows. By chance, one group's cows had higher pre-calving serum calcium. That baseline advantage makes that protocol look better in a plain ANOVA, even if the protocol itself did nothing. ANCOVA adjusts each group's observed mean upward or downward based on whether its baseline covariate was above or below the overall mean, leveling the playing field. Two rules are absolute. First, the covariate must predate the intervention. If it was measured after treatment started, it might already reflect the treatment effect. Including it then removes the very thing you're trying to measure. Second, the regression slope between covariate and outcome must be similar across all treatment groups. Test this by adding a treatment by covariate interaction term to the model. If that interaction is significant, the adjustment is different in different groups and ANCOVA is invalid. Acknowledge the limitation and consider stratified analysis. The chart consolidates the talk into a single decision pathway. Every time you're comparing group means, work through it. How many groups, paired or independent, baseline covariate to control? The paired design point is worth repeating one final time because it's so frequently underused. Anytime you can measure the same animal before and after, or match animals across groups on a relevant variable, use the paired structure. The power gain is real and often substantial, especially in small veterinary studies where every degree of freedom is precious. ANCOVA's 2 rules. Pre-treatment covariate, homogeneous slopes. Violation of the first rule, measuring the covariate after treatment starts, is the most common ANCOVA error and it invalidates the entire adjustment. Violation of the second, heterogeneous slopes, means the adjustment is working differently in different groups, which makes the adjusted mean an average of incompatible adjustments. Pause the video and try to work through the questions associated with this scenario. We'll then work through them together. This scenario tests ANOVA mechanics, Tukey's post-hoc interpretation, and the clinical need for ANCOVA in a single realistic case. Question 1 answer. Levine's test p equals 0.38 is non-significant, meaning there is no evidence that the variances differ significantly across the 3 diet groups. The equal variance assumption of ANOVA is satisfied. Proceed with standard one-way ANOVA rather than any variance-corrected alternative. If Levine's had been significant, Welch's one-way ANOVA would be appropriate. Question 2 answer. The significant ANOVA, p equals 0.001, tells us that at least one of the 3 diet means differs significantly from the others. It does not tell us which specific pairs differ. That requires Tukey's HST. We also cannot yet conclude that the differences are due to the supplement rather than baseline weight differences, given that group M started substantially heavier. Question 3 answer. Tukey's HSD. The critical difference threshold is 18.5. S versus H is 16 kilograms, less than 18.5. Not significant. S versus M equals 29 kilograms, greater than 18.5, significant. H versus M equals 13 kilograms, less than 18.5, not significant. Conclusion: the moderate supplement produced significantly higher final weight than the standard supplement. High supplement did not differ significantly from either standard or moderate. Question 4. Group M began the trial with average weights 25 to 28 kilograms heavier than groups S and H. Because starting weight strongly predicts ending weight, Group M's higher final weight is likely partly or entirely explained by its baseline advantage, rather than the supplement itself. This is confounding. The baseline weight difference creates the appearance of a supplement effect that may not be real or may be smaller than it appears. ANCOVA, with day 0 weight as a covariate, will adjust each group's final weight for where they started, producing a fair comparison of the supplement effect independent of baseline differences. Question 5 answer. ANCOVA conditions. First, the covariate, day 0 weight, must have been measured before the intervention began. Day 0 weight was recorded before the supplement protocol started. This condition is satisfied. Second, the regression slope between baseline weight and final weight must be similar across all 3 supplement groups. Homogeneity of slopes. Test this by fitting a model that includes a supplement by day 0 weight interaction term and checking whether that interaction is statistically significant. If the interaction is non-significant, slopes are homogeneous and ANCOVA is valid. If significant, the ANCOVA adjustment works differently in different groups and the analysis needs to be stratified or an alternative approach used.